The central problem of electrostatics is explaining action at a distance. If you place two charged particles in a complete vacuum, they will physically push or pull on each other. We have to figure out exactly how these invisible forces interact across entirely empty space. Charge is an intrinsic property of matter, existing alongside mass as a fundamental building block. Unlike mass, however, it comes in two distinct types, positive and negative. This animation illustrates the principle of quantization. Charge exists in discrete, indivisible packets, defined by the elementary charge of a single electron, roughly 1.6 times 10 to the negative 19th coulombs. Nature rejects fractions of an electron. They must snap to whole integer multipliers. Because these charges are discrete physical entities, they obey a strict law of conservation. An electrical charge cannot be created or destroyed. It is only transferred from one location to another. When we observe macroscopic charging, whether that's rubbing a glass rod with silk or inducing a charge from a distance, we are witnessing the mechanical relocation of these indivisible electron packets between objects. By tracking these individual packets, we can account for the total electrical state of any object, regardless of how many trillions of electrons it contains. We begin building our mathematical model with the simplest possible interaction, placing exactly 2 point charges in an empty void. French physicist Charles-Augustin de Coulomb observed that the force between these two charges follows an inverse square relationship. Doubling the distance between two repelling particles drops the force to a quarter of its original strength. This is Coulomb's original torsion balance. By measuring the slight rotation of that suspended needle against the fine scale, he proved that these invisible electrostatic forces could be precisely physically measured in a laboratory. To calculate this force, Coulomb's law uses a specific constant, designated as K. This is a composite value, calculated as 1 over 4 pi multiplied by epsilon naught. Epsilon naught is the permittivity of free space. It is a literal measure of how much the vacuum of the universe resists the propagation of the electric force. If you remove those charges from a vacuum and submerge them in water or glass, the force between them decreases. The new force is the vacuum force divided by the physical medium's specific dielectric constant. The electrostatic force is a strictly quantifiable vector. It is dictated by distance, the magnitude of the charges, and the material properties of the space they occupy. When we add a third charge to the void, we rely on the superposition principle. This rule states that the interaction between any two charges is unaffected by the presence of a third. We calculate each pair independently and add the vectors together. This diagram shows a specific three-body system. We have two identical positive charges, capital Q, fixed at a distance of r apart, with a third, unknown charge, lowercase q, placed dead in the center. We want this system in perfect equilibrium, meaning the net force on every particle is 0. Because the two outer charges are positive, they naturally repel. To stop them from flying apart, the center charge must generate attractive pulling vectors. It must be negative. We can lock this into an algebraic balance by focusing on one of the outer charges. We set the repulsive force from the far positive charge exactly equal to the attractive force from the center negative charge. By dropping common terms, we find that lowercase q equals capital Q over 4. The center charge must be exactly 1/4 the magnitude of the outer charges to hold the system still. By treating force strictly as independent, overlapping vectors, we can mathematically freeze a system of repelling particles in a state of perfectly balanced tension. Calculating individual vector pairs for the trillions of particles in a solid object is computationally impractical. Even for a supercomputer, the scale of the interactions quickly outpaces the utility of the point-to-point model. To solve macroscopic problems, we assume a single source charge alters the geometry of the space around it. We call this the electric field. Mathematically, the electric field is defined as the force exerted per unit of a positive test charge. We represent this as E equals F divided by Q naught. This graph maps the strength of that field against distance. Because it is derived from Coulomb's law, the field follows an inverse square decay. It drops off in a steep parabolic curve that approaches 0 at infinity, but mathematically never touches it. We draw these fields using strict geographic rules. Lines must originate at positive sources and terminate at negative ones. Their density indicates field strength, and because a single point in space can only have one force direction, field lines can never cross. By adopting this framework, we no longer track the position of every reacting particle. We simply map the mathematical distortion of space itself. We test this field model against the electric dipole. A dipole is a system of two equal and opposite charges, a positive Q and a negative Q, separated by a very short distance, which we call 2D. The strength of this system is measured by its dipole moment, a vector represented by P. By convention, this vector points strictly from the negative charge to the positive charge. This geometric layout sets up our challenge. We need to determine the net electric field at target point P, located at a distance x on the equatorial plane that perfectly bisects the two charges. First, we map the individual field vectors acting on point P. We draw a vector pushing up and away from the positive charge, and a vector pulling down and toward the negative charge. Using basic trigonometry, we split these diagonal vectors into their sine and cosine components. Because the charges are equal, the vertical sine components perfectly cancel each other out. The horizontal cosine components, however, point in the same direction and stack together. We can apply a binomial approximation for a short dipole, where our observation distance x is vastly larger than the tiny separation d. When we do this, the d² term in our denominator effectively collapses to zero, leaving us with an elegant final equation. The net field E equals kp divided by x cubed. Symmetrical opposing charges do not simply cancel each other out. Their slight separation generates a highly structured field that decays at the cube of the distance, dropping off significantly faster than the field of a single isolated charge. This 19th century laboratory reminds us that the ultimate purpose of calculating an abstract electric field is to predict the kinematic motion of physical matter. If you drop an electron into a uniform electric field, the field will exert a force on it. Because the electron is negative, it will instantly accelerate directly in the opposite direction of the field lines. We can bridge our electrostatics directly into classical mechanics. By setting the electrostatic force equation, F equals QE, equal to Newton's second law, F equals ma, we can solve for acceleration. It is simply the particle's charge times the field strength divided by its mass. With acceleration clearly defined, we can apply the standard kinematic equations of time, distance, and velocity directly to subatomic particles. But this brings us to the final boundary of our point charge model. We can perfectly predict isolated nodes, but we must also account for charge smeared continuously across a one-dimensional wire, a two-dimensional flat plate, or a three-dimensional solid volume. Solving these continuous geometries requires a model that measures the total flux passing through a surface rather than individual particle interactions.